This is the continuation of the 4.6 notes. So we're solving this log equation, and we're going to work on the left side a little bit, and then we're going to work on the right side a little bit, and then we're going to see what we have. So the left side can be simplified just a little bit by taking this power 2 up into the exponent location for 5. So this is going to become the log base 3 of x minus the log base 3 of, 5 squared is 25. All right, the right-hand side, what can we do here? This 2 can be brought up as a power on the 10. So now we've got the log base 3 of x plus 1 minus the log base 3 of 100, because 10 squared is 100. The left-hand side has the difference of 2 logs. We write that as the log of the quotient x over 25. The right-hand side is the same. It's the log of the quotient, log base 3 of the quotient, x plus 1 over 100. Now you have the log equal to a log. They're the same bases, and so they will eventually cancel out. And so you're left with the proportion x over 25 equals x plus 1 over 100. And we're solving for x in this case. So maybe cross multiply to get rid of the fractions. So that's going to give you 25x plus 25 equals 100x. And get all the x's on the same side. Let's take the 25x over to the right. So what is that, 75x? So 25 equals 75x. We divide by 75, we get x equals 1/3. X equals 1/3 does fit within the domain that's allowed, because plugging 1/3 back into the equation for x gives you the log of positive quantities. Number 50. Okay, so this is totally different. It's an exponential equation. We have to decide how we're going to go about solving this exponential equation. There are a few different schools of thought on this. Just for consistency, I'm going to use the same method no matter what the numbers are. And that method I'm going to use is taking the natural log of both sides. There are tips and tricks that I could explain to you if we were in class about what types of bases are more appropriate than others, but let's just keep it simple and always take the natural log of both sides. This is a good technique to use whenever you have an exponent that contains a variable. It's even better in this case because we have both exponents that contain variables. So here's my tip. If the variable, here, let's say it like this. If the exponent contain the variable, take the ln of both sides. All right, so the ln of both sides looks something like this. ln of 2 to the x plus 1 equals ln of 5 to the 1 minus 2x. You guys remember a property when you've got the logarithm of the logarithm of a quantity to a power. That power can be brought down in the front of the logarithm. So that can be done on both sides, right? So now we've got x plus 1 times the natural log of 2 equals 1 minus 2x times the natural log of 5. And you have got to put these expressions in parentheses. Otherwise, you will forget to distribute the logarithm appropriately. Parentheses are necessary. Okay, so I'm going to distribute like I just mentioned. Natural log of 2 times 1, natural log of 2 times x, and on the other side do the same thing. And now you've got this result. The next step you want to try to do is get all of the terms with x's on the same side. So locate where all of the x's appear. Okay, everything that's got an x needs to be on the same side. Everything that does not have an x needs to go to the other side. Okay, so I'm taking everything with an x, let's go to the left, and everything without an x, let's go to the right. So all my x's on the left. And all of the terms without x go to the right. You might notice that on the left-hand side, both of those terms have an x in it, right? That's why I put them over there. I'm going to factor out that x. Common factor, bring it out. And now that I've brought that common x out as a common factor, everything that's right here is a constant. That's just a big, ugly constant. So I'm going to divide both sides by that big, ugly constant. I'm going to stop there. There are some things you could do to simplify your answer, but it's really not worth it. If you can get this far, that's doing pretty good. So we can stop here. Call it a day. Okay, 58 is going to involve a trick. All right, you would not know how to solve 58 unless you had seen the trick done before. Here's the trick. Here's the trick. We're going to let y equal 3 to the x. What? Why would you ever know to do that? Experience, that's how I know that this is going to work. I see that the first term of my equation has a 3 to the 2x, and the next term is just 3 to the 1x. And I'm like, well, those are pretty similar, right? If those are pretty similar, I wonder if I can just simplify them somehow. And it turns out that you can by letting y equal 3 to the x. That means that y squared is equal to 3 to the 2x. You just square both sides. Squaring both sides of your let statement here gets you to this statement. And now you're going to substitute back into your original equation. The 3 to the 2x, we're going to call that y squared. And this 3 to the x, we're going to call that y. The 2 doesn't change. I just changed the equation into a quadratic, and it looks much more manageable. This is something that I can factor. Y plus 2, y minus 1. I get two answers from here, -2, +1. Circle those. Those are your solutions for y. Those are not your solutions for x. We have to go back and find what the x would be. All right, remember where we told, where we decided what y was going to be equal to? That little statement right there. We're going to go back there. All right, and this time we're going to say, well, if y equals 3 to the x, and I found out that one answer said y equals -2, well, that must mean that -2 is 3 to the x. Well, 3 to a power is always going to be something that's bigger than 0. I'm never going to get a negative answer. No matter what I try to use for x, I am not going to get -2 for this answer. This gives you no solution. No usable solution. Well, that takes care of -2. What about 1? Because y could have been +1, right? So that would say that 1 is equal to 3 to the x. So 3 to what power would give me a 1? 3 to what power gives me a 1? Maybe you're not sure. That's fair. You're not sure. So let's solve this equation now for x. Solve this equation. How am I supposed to solve for x? Well, I gave you guys a tip up here. The tip said that if the exponent contains the variable, take the natural log of both sides. Well, that's what I've got. So let's take the natural log of both sides. Natural log of 1 equals the natural log of 3 to the x. What's the natural log of 1? Natural log of 1, if you look way back in section 4.5 notes at the very beginning, tells you that the natural log of 1 equals 0. So 0 equals, we have another property that allows us to bring this x down in front. So this is x times the natural log of 3. You see it yet? We're almost there. We're solving for x. Get rid of the natural log of 3. Natural log of 3 is just a number. It's just an irrational number. And now I get x equals 0 divided by the natural log of 3. 0 divided by anything equals 0, and now you're done. X equals 0. This last example is very similar to what we just did with the whole let y equals some component. Here you have to be a little bit more crafty about it to understand what y needs to equal. Let y equal, okay, so here's a clue. Do you see the 6 to the x right here? That's your clue, okay? Knowing that that particular part of the problem is a 6 to the x, could you also rewrite the first term as 6 to the 2x? Would that work? Because 6 squared is the same thing as 36. So it works because 36 to the x is the same as 6 squared to the 2x. So we're going to make that a little adjustment in our minds. And we don't need to write anything down for it necessarily, but that's going to help you realize that y needs to be your 6 to the x. And so then your y squared would be your 6 to the 2x. Well, remember that that was 36 to the x. So it all works out. So my equation with my substitutions for y is going to say y squared minus 6 times y equals negative 9. And quadratic equations are solved by taking everything to one side so that it's equal to 0, and then either factoring or using the quadratic formula. This should factor. Yeah, this factors. Y minus 3 times y minus 3 equals 0. And so my solution for y is 3. Hopefully, that's the only solution. Hopefully it works. Let's see if I get a decent answer for x out of that. Well, go back up to where you made your let statement, and you said let y equal 6 to the x. Well, I just determined that y has to be a 3. Well, that means that 3 is equal to 6 to the x. All right, I'm trying to find out what x is. I don't have x yet. I'm going to solve this equation for x. So solve. It's like a problem within a problem. Solve that equation for x. Did you notice that the variable is up in the exponent? The tip that I gave you says when the variable's in the exponent, take the natural log of both sides. All right, we got ln of 3 equals ln of 6 to the x. How is that helpful? Well, there's a property of logs, because now we've got a log, right? There's a property of logs that tells you bring the exponent down in front. So now you have the log of 3 equals x times the log of 6. And now it's really easy to get the x by itself because natural log of 6 is just a number. And I can divide both sides by that number. And now I get x equals the natural log of 3 over the natural log of 6. And that's it. That is your answer. No way in a million years would I have guessed that to be my answer when I first solved this problem, but do the work and it comes out. All right, that takes us through all of chapter 4. You guys need to get yourselves on MLP and get that homework completed as soon as possible because the following week we are going to have our test over chapter 4. So get yourselves caught up over the weekend on this material.